Welcome to Ask and Learn.
So we're given a modified Tower of Hanoi problem where every we're solving for D disks was involved in both the second thing, like number two. So we're asked to find the recurrence relation for the number of moves required to solve for D disks with the restriction that you must use peg number two. Well, we know if there's zero disk, it's just zero moves. And then for D plus one disk, first you have to solve for D disks, and then you have to move the last one. So you would keep the bottom peg there and then move the other D disks to peg 3. So you move these all the way to peg 3. So then in order to do this, the number of steps to do this is S sub D. And then now you have to move the bottom peg, the bottom disk all the way from peg 1 to peg 2. Then you move this one to peg 2. So that's plus 1 move. And now you have to move these D disks from peg 3 back to peg 1 so that you can move the large disk on peg 2 to peg 3. So then you then take these guys back to peg 1. And that takes S sub D moves again. And finally, you move the largest peg that was on peg 2 to peg 3. So that's plus 1 move again. And then at last, we're just going to move all the D disks at peg 1 to the D disks at peg 1. We're going to again move them back to peg 3 so we can put them on top of the largest disk. And that requires S sub D moves again. So let's add this up. We have 3 S sub D plus 2. So that's the number of moves required to solve this with D disks. Next, we're asked to solve this recurrent solution to find a formula for the number of moves required to solve the puzzle for N disks. Okay, so we know for 0 disks it's just 0. For 1 disk it's going to be 2 moves because you have to use peg 2. In a regular game it will be 1 move. So the added restriction will be 2. And then for 3 disks there will be 8 moves. And 4 disks that will be 26 moves. It should be 2, should be 3. And notice there's a pattern here, so it's just S sub D is equal to 3 raised to the number of disks minus 1. And in the regular game, it was 2D raised to the D minus 1. So now all we have to do is prove that this formula actually works for all number of disks. So we're going to prove this by induction. And it's going to be similar to a proof of showing that it's 2 to the D minus 1 for a regular game. So first thing, we're going to let our hypothesis P of n equal the number of moves it takes to solve for D disks. Well, P of D in this case is equal to 3D minus 1. And then we have our base case. So let's use a base case of 0 disks. If there is 0 disks, well, that's just 0 steps. And this works from the formula we have. 3 to the 0 minus 1 is just 1 minus 1, which is 0. The base case works. Now for inductive step. Well, first you want to assume that our hypothesis P of D is true. And we want to show that P of D plus 1 is also true. So we want to show P of D plus 1. Well, P of D plus 1 is just 3 to the D plus 1 minus 1. So we want to show this is true. So this is our end result. This is what we're trying to get to. Well, if you have D plus 1 disk, you still need to keep the largest disk fixed and then move all the other disks to peg 3, just like from before. So you have peg 1, peg 2, peg 3. You have some number of disks. So you have D plus 1 disks. This is 1, this is D. So you're going to keep this bottom one fixed and move all of these here to peg 3. So that requires at least 3 to the D minus 1 steps from our inductive hypothesis P of D. And now the next thing you do, you want to move the largest disk to the second peg. And that's just one step there. And then after that, you want to move your D disks back to peg 1 to make room for the largest disk to go there. So that requires 3 to the D minus 1 steps. And that's from our inductive hypothesis P of D. And then finally, you want to move the largest disk to that third peg. So that's just one step. So that's moving this all the way here. And then you want to take these D disks back to peg number 3. So that's 3 to the D minus 1 steps from our inductive hypothesis. So then solving S of D plus 1. Well, first we did S of D. This is S of D. That's why I'm writing S of D. And then we did 1. So we did 3 S of D plus 2. We did 3 of these steps here. And then we had 2 single steps here and here plus 2. And this is just equal to, well, we have 3 times 3 to the D minus 1 plus 2. That's 3 to the D plus 1 minus 1 plus 2 is equal to 3 to the D plus 1 plus 1, which is what we wanted to show. recall from over here, we wanted to show that p of d plus 1 was true, and this is p of d plus 1 here. So we've shown that it's true. So we know p of d plus 1 is true, and we can conclude p of d is true for all the, and that's how you do the proof. And we still have to do two more parts. We have part C, which asks us to find the number of different arrangements there are for the n disks on 3 pigs so that no disk is on top of a smaller disk. So no disk is on top of a smaller disk. Well, you can just randomly assign disks to pegs, but then order matters because you can't have a smaller disk be below a larger disk, so order matters. So this is going to be a permutation where order matters. And repetition is also allowed because let's say you have 5 disks, there's only 3 pegs, so you might have more than one disk to be on a peg. So then since order matters and repetition is allowed, by definition, that's just n raised to the r. And here n is going to be 3, the number of spaces you have that you're sorting by, which is 3, because there's 3 pegs. And then raised to d, which is the number of disks that you're arranging. So that's part C. Now part D asks us to show that every arrangement of these n disks occurs in the solution of this modified form of the puzzle. From part D, we know that S of D plus 1 is just equal to 3 to the D minus 1 plus 1, which is equal to 3 to the D. And every arrangement must be different from each other, because otherwise then you're just repeating moves, so you're not solving the puzzle efficiently. So if you start with the initial arrangement 1, then the moves you make give you 3 to the D minus 1 different arrangements. So you have the initial arrangements and the 3 to the D minus 1 arrangements you made. So you get arrangements are going to be equal to 3 to the D minus 1 plus 1, which is just equal to 3 to the D arrangements. So that matches our answer for part C. So there's 3 to the D possible arrangements and 3 to the D different arrangements as well. So that's how you do parts A,